In the figure shown, S is a large non-conducting sheet of uniform charge density rho. A rod R of length L and mass m is parallel to the sheet and hinged at the midpoint. The linear charge densities on the upper and the lower end of the rod are as shown in the figure. On the upper end it is lambda, and on the lower end it is minus lambda. Find the angular acceleration of the rod just after it is released. Now let me consider that this is a infinitely long sheet. Okay, so the electric field will be uniform. Okay, let us say this is hinged at O. Okay, and the configuration at the top end, it will be equal to lambda, and the charge distribution is equal to minus lambda. So there are positive charges over here and there are negative charges at the bottom. So this positive charges, since the electric field will be in this direction, the positive charges will experience a force in this direction and the negative charges will experience a force in opposite direction. Due to this, there will be a torque produced. We have to find out the value of the torque for this entire rod. Okay, let me consider a small charge dq on the upper section of the rod. Okay, now the electric field along this direction due to an infinitely long rod will be equal to E will be equal to sigma divided by 2 epsilon naught. Okay, so the force experienced by this small charge dq will be equal to, the force experience will be equal to E into q. Okay, or E into dq. This is the small force experienced. Okay, this is the small force experience. Due to this, let us consider it is at a length L. Okay, let us consider it is at a length L from the center and there is a small length dl. Okay, so the linear charge density lambda can be written as dq divided by dl, or it can be written as total charge. Let the total charge be equal to q divided by l. Okay, so now over here the torque experienced by this small part will be equal to the small torque over here will be equal to force into small force into perpendicular distance. Okay, perpendicular distance over here is equal to L. The small force experience is equal to E into dq. Okay, it will be equal to into multiplied by L, which can be written as E is written as sigma divided by 2 epsilon naught. So it will be equal to sigma divided by 2 epsilon naught into dq into L. Now dq can be written as lambda into dl. Okay, so this is written as sigma divided by 2 epsilon naught into lambda into L into dl. Okay, this is the total torque, this is the small torque experienced by this small section of the rod. If I want to find out the entire torque, I need to integrate this part, small torque over here, which will be equal to sigma divided by 2 epsilon naught and lambda will be constant over here. Okay, sigma divided by 2 epsilon naught and lambda will be constant over here. It will be equal to L. Okay, so integration of L dl. So integration of L dl will be equal to, the torque experience will be equal to sigma lambda divided by 2 epsilon naught. Integration of L will be equal to L square divided by 2. Okay, it will be equal to L square divided by 2. Okay, so it will be equal to from 0 to L. Okay, so basically it will be from over here, it will be from 0 to L. Okay, so 0 to L is the length of the rod over here. Okay, 0 to L is the length of the rod. So basically it will come out to be sigma lambda divided by 2 epsilon naught into, over here it will be equal to L square divided by 2. Okay, now this is the torque experienced by one end of the rod. Similarly, if I consider for this given configuration, if I consider the torque experienced by the other end of the rod, okay, if I consider the torque experienced by the other end of the rod, it will be equal to, over here it will be equal to the same torque. Okay, the same torque is experienced. Okay, the same torque is experienced. Okay, so the total torque, this is by the one end of the rod, the same torque will be experienced because due to the positive charges this rod tends to move in the clockwise direction, and this at the rod that is due to the negative charge, it will experience force in the opposite direction, and it will also rotate the torque, it will also rotate the rod in the clockwise direction. So basically the total torque will be equal to twice this value, which will be equal to, the total torque will be equal to sigma by lambda into 2 epsilon naught into L square. Okay, over here it will be equal to sigma lambda divided by 2 epsilon naught into L square. We have to find out the angular acceleration at an instant. Okay, now the angular torque will be equal to I into alpha. The torque is already given sigma lambda L square divided by 2 epsilon naught. Let us consider the mass of the rod and the length of the rod. Now since the rod is rotating about its center, it will be equal to ml square divided by 2. Now the upper end of the rod, okay, the upper end of the rod over here, okay, okay, the entire length of the rod is equal to L. Okay, the entire length of the rod over here is equal to L. So this limit should be equal to L by 2. Okay, so it will be multiplied by, so basically it will be equal to half end of the rod, so it will be equal to L square by 2. I will multiply, so I will get L square by 4. So I will get 1 by 4 over here. Okay, and the moment of inertia of the rod will be equal to ml square divided by 12 into alpha. Okay, so this part will be equal to 4, this will be multiplied by 3, L square and L square will get cancelled out, alpha will be equal to sigma lambda divided by 2 epsilon naught into 3. Okay, so this will be the total angular acceleration, initial angular acceleration experienced by the rod. Mass will also be in the denominator. Okay, so this is the initial angular acceleration experienced by the torque, which is equal experienced by the rod, which is equal to 3 sigma lambda divided by 2 epsilon naught into m.